In Chapter 20, we'll be talking about magnetism. So how do we produce magnetic fields? Very similar to electric fields. There are going to be a lot of similarities here as well. We're going to first use magnets to produce magnetic fields. Turns out that moving charges or currents can also produce magnetic fields. So we'll take a look at the magnetic field due to wires. And also we're going to find out that a electric current in a magnetic field is also going to feel a force. So we'll take a look at the force of a current, a charge, and between two parallel wires. If a current carrying wire can produce a magnetic field, it turns out that we can actually build these things called electromagnets by essentially wrapping a wire around itself, creating a solenoid. Take a look at Ampere's law and how we can have torques on loops. Now when we talked about electric charge a couple of lectures ago, we said, hey, we can have a positive charge and we can have a negative charge, and like charges are going to attract or repel, and unlike charges are going to attract. The same is going to be true for magnets. Magnets are going to have two ends. We're going to call these poles, north and south. Very typically the north is called positive and the south is called negative, and like poles are going to repel and unlike poles are going to attract. So you put two norths together, it's going to repel. Same for two south, they're alike, they're going to repel. You bring a north in close to a south, and it's going to attract. One key difference between charges and magnets is, suppose I had an atom which was a positive charge with an electron, say, kind of whizzing around it. I could actually separate these two guys out. I could take this electron, pull it way over here, and disassociate it with the positive charge. So I could separate charges. I could have single charges. However, if you consider a magnet and you take it and you cut it in half, just like this, you're going to actually end up with two smaller magnets, each with a north pole and with a south pole. Even if you were to split it in half again, you would end up with four magnets, each with north and south poles. So we will never be able to separate out the north pole from the south pole, so there will not be magnetic monopoles. And everything we learned about electric field lines is going to apply to magnetic field lines. So we had a positive charge, and we said my electric field lines are going to be going away from it, kind of in that direction, kind of like this. Magnetic field lines are going to look almost identical. Remember I said that we're going to treat the north as positive and the south as negative, and so magnetic field lines are going to leave the north and they're going to come back into the south. One difference between electric fields and magnetic fields is, again, this idea of no magnetic monopoles. Magnetic field lines are always going to be closed loops. So, this line that leaves the north is going to come back into south. This line over here is going to come back into south. Again, leaving north, coming into south. Even these lines that are kind of leaving the screen, they're going to kind of come back over here and come back into the south. If we were to kind of chuck a whole bunch of iron filings onto a magnet, you're going to see that these iron filings are going to line up along the lines of magnetic field. And kind of similarly, if I said that this was the north end of a magnet and this was the south end of a magnet, if we take a look at a compass, all a compass really is a magnet. And so here, the south end is going to be attracted to the north end of the magnet, the north end is going to be repelled, and this magnet is going to also line up with the magnetic field of this magnet. And this is more or less how we can use compasses to navigate. The Earth has got some magnetic field associated with it. Essentially, kind of picture some big bar magnet inside of Earth. Not quite true, but good enough. And this magnetic field is going to be leaving the north and kind of coming back into the south. As I said in the last slide, a compass is just going to have a magnet on there, and that magnet is going to line up with Earth's magnetic field. But kind of something to keep in mind is this magnetic field is this magnet in the compass is going to be the north part of a magnet. It's actually going to be attracted to the south pole of the magnet that's inside of Earth. So kind of a mind twister to think that the North Pole is actually going to be a south magnetic pole. Now pretty much for everything we're going to talk about in this class is we're going to talk about uniform magnetic fields. So magnetic fields that aren't really changing in magnitude or direction. Now the reason why we do that is because it becomes a real bear to deal with magnetic fields that are changing. Kind of, what we're kind of saying here is that we're going to look at magnets that are really, really, really big in extent. And the magnetic field is going to leave the north and approach the south pole of another magnet. And kind of in the middle right here, the magnetic field is going to be uniform. So everything that we're going to be dealing with is kind of going to be in this regime right here. We're going to kind of ignore the fact that there's kind of wobbles out here on the side. Now something that we've learned that's actually quite powerful is that electric current can also produce a magnetic field. Actually, to be more specific, it's going to be not necessarily electric current, but moving charge. Remember that the flow of charge is going to be called current. So moving charges, currents, can produce a magnetic field. We can kind of see this if we were to say, hey, we have a wire right here. We're going to run some current through there and put kind of compasses around here. These compasses are going to line up with a magnetic field. Turns out that this magnetic field is actually going to be, kind of circular. If we were to throw some iron filings, you can see that this magnetic field is going to be circular around this wire. How can I determine the direction of the magnetic field? Well, we have to do what's essentially called the right-hand rule, which is going to say, hey, I'm going to take my thumb and I'm going to point that in the direction of the current. And then the direction that my fingers can kind of curl around this wire, that's going to be the direction of the magnetic field. Now, magnetic field, much like electric field, is going to be a vector, so it's going to have a magnitude and a direction. The symbol for magnetic field is going to be this B right here, and you can kind of see that here we've got our fingers kind of curling around the wire in that direction, so my magnetic field is going to be curling around in circles like this. Same for this case over here. These compasses are all kind of lining up in a circle, and the magnetic field is going to be kind of in the counterclockwise direction around this current carrying wire. Now, when we talk about magnetic fields, again, it's going to be the symbol B. I'm going to put a little vector sign over it. Magnetic fields are going to have a unit of a Newton amp per meter. That's a weird, funky unit. Very often, we're going to use the unit of Tesla, and a Tesla is a huge magnetic field. Much like with electric fields, we're going to be talking about micro, nano, millitesla, stuff like that. Sometimes, not very often, you may see the unit of a Gauss, which is going to be 10 to the minus 4th Tesla. And as I said, we're going to be working with small amounts of magnetic field, so a Gauss kind of takes the number down a little bit. And just to drive home the point, direction is going to be very, very, very important in this chapter and the next couple of chapters. So make sure that you're good to go on this right-hand rule. The right-hand rule is going to tell us the direction of the magnetic field. And again, we're going to take our thumb and we're going to point that in the direction of the current, and then look what direction our fingers kind of wrap around. So if we had a wire kind of like this, and we said, hey, we've got some loop with current flowing through it, I take my thumb, I point it in that direction right there. What direction do my fingers curl around in? Well, they're going to be curling around in that direction right there. So the magnetic field is going to be in that direction. You can kind of convince yourself at the bottom of the loop, the current's pointing in that direction. You kind of have to wrap your hand around at some weird angle. You can see that the magnetic field is going to be in this direction right here. Since we know that a current carrying wire is going to have a magnetic field surrounding it, well, what would happen if we just kind of brought it into the magnetic field of another magnet? It's going to behave just like two magnets. There's going to be an attractive force or a repulsive force. Key thing is what direction is that force going to be in. So make sure that you're good to go with figuring out that direction. We again have to use the right-hand rule, where if we take our index finger and we point them in the direction of the current, there's only one way that I could curl them into the magnetic field. So kind of picture my fingers sweeping from the direction of the current into the magnetic field. The direction that my thumb is left pointing is going to be the direction of the net force. So kind of think of the current being in this direction here, and here we have the magnetic field. The only way that I can have my index finger pointing in that direction and then kind of sweep them into the direction of the magnetic field is if my hand looks like this right here. The force is going to be up in this case. If we consider this case right here, we take our index fingers, point them in that direction. The only way I can curl them into the direction of the magnetic field is if my thumb is down. Kind of like I'm showing right here where I did a little cut and paste magic. So that's the direction of the force. Well, how about the magnitude of it? Well, it turns out to be pretty simple. I'm going to say that the force, again in newtons, is going to be the current in amps, multiplied by the length in meters, multiplied by the magnetic field in Tesla, and then sine of the angle between the wire and the magnetic field. So kind of conceptually here, I've drawn a magnetic field going from the left side of the page to the right side of the page, and a current carrying wire coming up it. And then the angle between them is just going to be that angle right there. You can kind of see that if the wire was, that was pretty bad, if the wire was running in that direction, the angle between the magnetic field and the current carrying wire would be 0, so the force would be 0, but we would experience a maximum force if the angle was 90 degrees. Keeping in mind that currents are just moving charges, we could also say, hey, we can go ahead and write what the force is on a moving charge. That's simply going to be the charge in coulombs, the speed in meters per second, and then the magnetic field, and then the sine of the angle in between them, are pretty much identical to what we dealt with wires. Keep in mind that this charge must be moving. If we just have a charge that's just kind of sitting there inside of a magnetic field, it's not going to experience a force. It will experience a force if that was an electric field, but not a magnetic field. Only once it starts to move does it experience a force. For the direction, we again have to use the right hand rule, where what we do is we point our fingers in the direction of the particle's velocity, and we kind of curl them into the direction of the magnetic field, and the force is going to be the direction of our thumb. So convince yourself that you can do it for a positive charge right here. Something to keep in mind is we can also have negative charges. So with a negative charge, what you have to do is essentially what I do is I figure out for the positive charge, and then I just kind of flip my thumb over. Kind of an interesting consequence of a charged particle moving in a magnetic field is that the force is going to be perpendicular to the velocity. It's also going to be perpendicular to the magnetic field. But because the force is perpendicular to the velocity, it can't actually do any work on this object, so it can't change its kinetic energy. So the speed is actually going to be equal to a constant. The velocity will simply change the direction. Now here we have the magnetic field going into the page. That's represented by these X's. If you ever see magnetic field coming out of the page, it's either going to look like that, or may just be a simple dot. I'll leave it up to you to convince yourself that the direction of the force should be towards the center here. Keep in mind this is a negative charge, so make sure you get some practice doing the old right hand rule. And this is going to be a center pointing force. This looks an awful lot like the centripetal acceleration. If I said what is the sum of the forces on this particle, that must be equal to its mass times its acceleration, which is going to be its mass velocity squared divided by radius. Now, what is the force? In this case, the angle is 90, and so we're simply left with the charge multiplied by the velocity multiplied by the magnetic field. So we could actually figure out the radius of curvature here, where it's going to be related to the mass, how fast the electron is moving, the charge, and the magnetic field. So we could actually kind of figure out what this radius is, knowing all of those other parameters. Just kind of some notes on problem solving with these magnetic fields and forces. Always remember that the force is going to be perpendicular to the magnetic field direction. It's never going to change the speed. So force is going to be perpendicular to the speed, which is going to be perpendicular to the magnetic field. We have to use the right hand rule to determine it. So again, very important concept. And then the equations that I've given you only give the magnitude. We have to use the right hand rule to get the direction. And just to highlight once again how important this right hand rule is, table 20.1 kind of summarizes everything that I've already said about using the right hand rule. So make sure that this is in your notes and in your head.